Okay, now we have a situation where we have X, Y, and Z axes, and we have a loop of radius 10 centimeters in the XY plane with a current of 12 amps, I believe, yes, same old 12 amp current. Running around the loop. So what we want to do is we want to consider a 1 centimeter segment somewhere on this loop. And we want to calculate the field at the origin due to this 1 centimeter segment of current. Well, our I delta L is going to have magnitude, same as it was before, 12 amps times 1 centimeter. We're going to have to get the direction vector of the segment. And we're going to need what else in order to calculate this? Now we have I delta L cross R over R divided by R squared. Well, if we get I in the delta L vector, it's going to be clear that the only thing we need in addition is the R vector, so that we can calculate the unit vector R divided by its magnitude over R squared. Okay? So what is the R vector going to be? You should pause and think this through. Well, the R vector goes from the segment to the field point. So the R vector is going to go here. Now, maybe I didn't say it. We consider this 1 centimeter segment to be such that some vector from the origin out to a point of the segment makes angle theta with the positive x-axis. As it's stated in the problem, the coordinates are 10 centimeters theta, and theta is any angle, okay? And that those are polar coordinates. Okay, so in polar coordinates, this is what you got, 10 centimeters here, angle theta as measured counterclockwise from the positive x-axis. Okay, so, well, what is the R vector in this case? Well, you want to stop and think about that. I'm going to write a little bit here. Okay, now I previously wrote delta L without the multiplication by 1 centimeter, but obviously this isn't a delta L. We have to multiply it by a distance, and of course the length is 1 centimeter. So it's going to be 1 centimeter times this unit vector. And I think I discussed that. I've written down a couple of things, but let's make sure why delta L is equal to this. Well, actually, I'm going to let you work that out. Delta L is in this direction. I've drawn a head on this arrow, and you can confirm by any number of ways the right angle between the radial line and the tangent line, etc. You can easily verify, or you should be able to verify, whether easily or not, that delta L is negative I sine theta plus j cosine theta multiplied by 1 centimeter. There are all kinds of tools you can use to verify that. Try to find the simplest one. Okay, now when I multiply that out, when I do the cross product part, basically the numerator right here before I multiply by k prime over r squared, okay, I get the cross product, and I wrote that as a multiplication rather than a cross product. So let's make that look like a cross product. Okay, I delta L cross R vector over its magnitude. The I delta L is going to have a magnitude. Well, I is 12 amps, and we multiply that by the 1 centimeter, which is 0.01 meter, and we get 1.2 amp meters. I don't know if you can read that. It's pretty hard, but it's 1.2 amp meters. The same thing that we had up here. But it's not 1.2 amp meters times J now. It's 1.2 amp meters times the unit vector in the direction of delta L. And here's our unit vector in the direction of a tangent line to the circle. And we cross that with the R vector divided by its magnitude, which is just the unit vector from the segment back toward the origin. And we get, well, that's going to be negative I cosine theta minus j sine theta. Now, when you get done with that, you are going to find that this cross product is going to have direction, well, it's pretty clear this direction is going to be direction of delta L cross R, which is going to be vertically upward. So this cross product had better come out with a plus K. And it turns out it does. I crossed with I is 0. I crossed with J is K, so that the I sine theta and the J sine theta, both being negative, are going to give us sine squared theta. And then the J crossed with negative I, here's J crossed with negative I, also gives us a K vector. And we're going to have, a negative cosine squared. Something's wrong. Let me fix it real quick. Okay, I've looked at this all I'm going to look at it, and I still can't reconcile it. Negative I cross negative J is positive K, so we're going to get a positive sine squared theta times K. J cross with negative I is negative K, and that gives us a negative cosine squared theta times K. And sine squared theta minus cosine squared theta doesn't equal 1. However, this has to be 1. So let's see if you can get me out of this. But this is going to equal 0.12 amp meters times K. And I'm real confident of that because I know that this vector crossed the delta L vector crossed with the R vector does give us a positive K, and everything we do here should result in a positive K. So I'm not sure what I'm saying wrong here. Write it out yourself and see if you can make it work. In any case, we get this. Now I'm not going to work out the rest of it, just I'm going to observe that this gives us 0.12 amp meters times K, just as this calculation did. Okay, this is 0.12 amp meters times J cross I, and actually in this case, well, it gave us a negative K, but here it's going to be a positive K. The whole calculation then is going to come out the same. The distance, the magnitude of the R vector is the same as it was here, and of course this constant is the same, and everything is going to come out the same magnitude except it's going to be positive. We're going to get a positive 1.2 times 10 to the negative 6th Tesla times K, so that we get this, and I'm going to call this delta V equals 1.2 times 10 to the negative 6th Tesla times K. That's the contribution from this delta L. Now, this doesn't depend on where this is. Theta could be any angle between 0 and 2 pi radians, or 0 and 360 degrees. So this is going to be the same result for any 1 centimeter segment of this loop. So if we add up all the contributions from 1 centimeter segments, we should get the total magnetic field at the origin. Every one of them is going to give us 1.2 times 10 to the negative 6 Tesla times K. So all we have to do is figure out how many 1 centimeter segments there are around a loop of radius 10 centimeters. And that's going to be, well, the circumference is 2 pi times 10 centimeters, 20 pi centimeters. There are going to be 20 pi of these. So that the delta B from the whole loop is going to be 20 pi times this. And I'm going to write that down. Okay, so I've written that down. There are 20 pi such segments and so forth. And then I'm going to say, well, so that's the magnetic field at the center is going to be then 20 pi times what we got here for the whole loop. And I'm going to write that here now, the ratio of the two vectors, the yellow delta B vector and the big B vector. The magnetic field at the center is going to be approximately, I think maybe 7.6 times 10 to the negative 5th K Tesla. And that would be this vector. And that's an important configuration. You want to understand that. And hopefully you'll figure out what went haywire down here, but this is, I believe, the correct solution.